Hi everyone, my name is Orhan and I'm Android developer at Berlin and I'm also Android Google developer expert. Well, today I will speak about the life of APK and well, before actually starting the APK, how many of you have no idea about Android? Okay, just two, that's good. And how many of you actually like magics or magicians? Well, quite a bit. Well, so as do I. Well, as a person, I like magic. And I like magic because the way it happens is mystery. So something happens and you just like these things and you just care about the output. You don't care about the internal details. Well, it's the same for the users. When the users display your application, they actually don't care about what you did. And they just care about the output. Because for them, most of the stuff that you did is actually magic. But do they care? No. So for the user, when they display your application, for them, only the user experience starts. So it's the beginning of user experience. But for developers, actually it's end of the APK. So as a developer, we hate magic. And if you have developed a simple application, probably you already revealed the first one. So as I said, for the users, displaying a screen is the beginning of the user experience and the end of the APK. Well, every ending has actually a beginning. So writing code is a beginning for us. And if you already did something, you already know this magic and you relive it. We just write the Java code and we create some resources and we have the Unread manifest file. And the next step is the assemble. So we need to put everything together and upload it to Play Store or do something. And some developers actually do it manually. They just assemble release if you are using the Gradle. And some others just use the continuous integration, which is you just push your code and the continuous integration does the job for you. Well, actually that's it. You don't do anything else. But in the behind, while doing the assemble, there are a lot of things happening. Well, the first one is the compiling. So it's like you understand the Java code, right? And when you put the resources, you also understand what it is. And you also understand the Unread manifest. Because you can just see what is happening by just looking at the code. The problem is the machine does not. I mean, machine don't know what you are doing. So machine speaks a different language. So we need to do something about this. So when you do assemble language, assemble task, you actually translate this code into something else. So that's what the compiler does actually. Translate one language to the another. And in Android, actually in this process, there are many compilers. And the first compiler is compiling your resources. Well, we understand these resources, but the machine does not. And also, we use some spaces, some extra code, which is not necessary for the Android system, because machine don't care about your space or your readability at all. So in Android, we have some compilable code, which is under resources, and there are some non-compiled code, which is under your res and row. And also Android manifest.xml is also a resources. So the AAPT, which is Android Asset Package Tool, just compile this code in a binary format and just decrease the size, and the machine can understand this language. And it produces three files. Resources in binary format and resources.arsk, which contains the relationship of these layouts. For example, when you have the layout width and you just point something else, the resources.arsk just contains the information. And also the r.java, which we use it in the Java code to access resources in an easy way. Well, speaking of r.java, well, I don't know if you already just checked what it does or how it looks. The code just generates a class, and this class contains a bunch of classes. And this classes contains the numeric integers. But is it random, or have they produced this one? Well, actually, it has a meaning. So whenever you use the AAPT, it generates a random number, kind of, but it has a meaning. And this integer number is 32 bits, so each package, each number contains some valuable information So the Android can use in the further. So it contains the package, and it contains the type of your resource, and it contains the name of your resources. So for example, animation. So the package is the same for all resources, so it's fixed, and it creates one integer for the anim. It's your animation folder, it's the type, and your name is like fate.xml. So the next is layout. It's a different type, so it just increments your value, and it starts with the name with the 0 again. So if you have the same type and the different name, so it just increases the second one. So we also have inter-process communication if you are using the AIDL. Well, it's the same. You can understand the AIDL, but Java does not. So you need to translate this language to Java. So AIDL compiler actually compiles this code and generates a Java file. So now we compiled the resources, we compiled the AIDL, but we have the Java source code. So we also need to translate this language so the machine can understand. Well, the good thing is Android didn't create their own compiler. It uses the Java compiler, which comes with the Java development kit. So the Java C actually compiles all your Java code into the bytecode, which contains in the class files. And each class has an individual file. So if you have the main activity.java, it has an individual class file. Well, but the question comes, what if I have anonymous class or inner or static class? So it will be one file or just bunch of file class. Well, the same rules is here. The rule is simple. Each class will have an individual file. So we have 4 classes because each class contains information about your Java source. So class file is actually contain the bytecode, and this class file contains every information about your source, such as constant pol, super name, the class name, and the methods, fields, everything. But the thing is, for example, when you translate one language to another, you just don't directly translate it, right? Because you may have some words in the language, but the target language maybe don't have it. So you need to do some work around. You need to do something about this. Well, the compiler is the same. When you translate something, you need to do something about this. And in Java, for example, we have the generics. And the generics are introduced in Java 1.5. So in order to backward compatibility, they do something during the compilation. So they just do the simple thing. They just use the same format when they had before 1.5. And also for the optimization. When you translate one language to another, you don't do it directly. You need to influence the culture. You need to influence the environment. You need to do something that the target could understand you better. And the same goes for here, for the compiler. In Java code, for example, you can concat 2 strings just doing like A plus B. But it's not very optimized for the compiler, for the machine. So the compiler converts your code into something else that machine can understand easily in an easy way, and in the terms of performance, it's better. But the thing is, for example, we have now bytecode, which is another language, and machines understand this. But the thing is, not every machine understands this language. But our idea, our practice is just write code once and run it everywhere. So what if all machines don't understand this code? Well, how can we do that? So we are using the virtual machine. So virtual machine is like an abstraction of the underlying operating system. Well, there are 2 kinds of the virtual machine. One of them is the system virtual machine, which you probably already know. You can use another language, operating system, actually. And the second one is the process virtual machine, which we are interested in. And the process virtual machines are basically cloning in the process and use the same resources, so you could just run every application in the underlying operating system. And the process virtual machine has 2 kinds. Well, one of them is stack-based and register-based. And before explaining these virtual machines, This is like a very simple formula. So 10 plus 5 equal to 15. equal to 15. So 10 and 5 are here operands, and the plus is the operator, and the 15 is the result. So each virtual machine actually has a different system for calculating logical and arithmetical operations. So stack-based actually, it comes from the name. It uses stacks for the logical and arithmetical operations. So for example, when we want to calculate 10 plus 5, first we pop 10. Then we pop the 5. Then we add both of them into another one, and we push it back. So we used 4 instructions just calculating one simple arithmetic operations. So this is the stack-based. But there is also another one which is register-based. It uses registers. So every operand has an address. So you don't need to use the stack. You can just access all of the operands by just using their address. The disadvantage of this is you need to have more space because you keep the address. But the stack-based actually didn't need this kind of information because you just pop the stack and you get the operand that you want to use. And the same calculation. So since we know the address of the operands, we could just use them and push them together. So it's just one instruction. And the register-based is actually faster than stack-based because of this. It just uses less instruction, so it's faster. But it has also this advantage of this keeping all the addresses. And we also need to use a specific virtual machine just for our bytecode, which is the Java virtual machine. And so each class that we had for the bytecode, we also need an entry point for them, and it's the class loader in the Java JVM. So our class files are loading in the class load, and it goes to the runtime data area, which keeps our memory, heap memory, stack memory, and other. Before the Java 7, it's like PermGem as well. And the execution engine just executed. So we have the main class now, a bunch of classes from our source, but it's still not complete because it's not machine code. It's an intermediate code. So we need to execute this code. So we need to do another translation to the real machine code. But the JVM does not work like compiler. So it does not compile all of the Java source into the machine code. So it happens in the runtime, and it uses the Java tool, which is interpreter. The difference between compiler and the interpreter is compiler gets all input all together, and they compile the whole code and give as output. But the interpreter works a little different. So it reads your code line by line and also at the same time execute it. So you could just notice that you have to do the same thing over and over again, even if you use the same methods. So they introduced another compiler in order to increase this performance, which is the just-in-time compiler. So whenever you translate one line and execute it, just-in-time checks the data and see if it is frequently used. It puts your machine code into cache. So next time when you use it, it just reads from the cache. So it's faster. So it just checks the lookup table, find your machine code, and just run it. For example, you may notice for the for loop, when you use the size in your for loop, it actually doesn't calculate this size all the time, just once. And the next is using from the cache. Well, it still uses something. But when the mobile are introduced, JVM wasn't good enough because it's meant to use for the desktop, for the powerful devices, but the mobile didn't have this powerful hardware at that moment. So they had to do something. So they introduced the Dex Format, which is another intermediate code. So all your classes are translated into a single file. But basically, it's almost the same with the classes, but more optimized in the terms of the space. So the Android build system uses the Dex compiler and gets all your classes and translate all of them into one single file, which is the classes.dex. What the good thing is, it's more optimized. It uses less space, and it's actually even faster. And in this step, there are actually some other things happening as well, like your for ProGuard. It happens in this step. And also, if you are using the Jacoco, it's the same. It happens in this step. And if you want to introduce like another Dex, you have to do it before doing this. And so we translated to another language. We had this Java bytecode, now we have the Dex bytecode. So it doesn't run on the JVM. So we need to use another virtual machine, which understands our Dex code. So Unread uses the Dalvik virtual machine, which speaks the same language with the Dex format. And it uses the just-in-time compiler, which is like good in the terms of performance, and also register-based, which is faster. And just a note, and each process has used one virtual machine, so they could just separate every application from themselves. And our biggest problem, if you had, I don't know if you just had it, but the Dalvik virtual machine, not the Dalvik virtual machine, but Android has this problem. You cannot have more than 65K reference count. Well, it's not the problem of the Dalvik, or it's not the problem of the Dex file. You could have many methods in your Dex file, or Dalvik virtual machine could just execute all of them. The problem is, they just set this instruction, and they said you could just have 16 bits of reference index. So when you calculate it, it becomes like 65K. But there are a bunch of solutions that you could use, but that's the main problem. Then, when the hardware gets powerful over time, but they introduced another virtual machine, which is the Unread Runtime. There is some significant changes, and one of them is like they changed the compiler. So we used the just-in-time, but Unread Runtime used ahead of time. So the difference is, when you install your application, all your bytecode translated into the machine code in the installation time. So that means you will have longer installation, and you will use more space, but it will run faster in the runtime because it will be less CPU cycle and also faster. And also, since you use this less CPU cycle, it also uses less battery. So it's actually good in the terms of everything. Well, when they introduced it, they also said that, well, when you boot your phone could be a little slower. But I don't know if it's the same now. And also, they improved the garbage collection. So you have now less post time, so which is great. So now we have everything actually. We compiled every code, we compiled the resources, and we have a bunch of folders. So this is actually what the virtual machine needs, that's all. But could you just upload all files together somewhere? It's actually hard. So you need to do something about this, and it also has big space. So you just use the basic thing APK builder tool, which just zips your code and decreases the size. And now we have the APK, but we have a little problem on the security. How would you make sure that your APK doesn't change, your code doesn't change during the transition, during your upload? Well, you have to sign it. So when you use the jar signer, you sign your application, each file in your APK has a checksum, and it uses the RSA, and it makes sure that your files didn't change at all during the transition, which is very important for the security. Now we have the signed APK. We made sure that it's secure, and it's a single file, and decrease the size. But there is another problem. We have the resources, right? And these resources are accessed by multiple processes. So for example, during the installation time, installer accesses your Android manifest and gets the permission and other stuff. So it accesses your resources. And secondly, launch your application, access your application icon and the name. So it accesses your resources. And the system also accesses your resources because it needs your application icon, application name, or etc. for notification and other stuff. And also, the last one, your application also accesses your resources. So that means you need to do something about your resources because every process accesses your resources. Well, the good thing is we have the solution. You could just zip align them. That means before zip align, whenever you try to access your resources, it goes through all the files and finds this access. But if you align them, Android uses the 4-byte boundary, which is memory map your resources, it accesses directly. So it has a significant change actually. So it's faster on the runtime and it uses less CPU. So now we have signed and we decrease the size and we also align. So it's perfectly fine and ready to upload. So we just upload it to Play Store or whatever place and that's it. So as a developer we did everything. So it's ready. Now the installation time. Let's say users like your application somehow and wanted to install and click the install button. The first thing happens is it downloads your APK. Of course, depends on your permission and other stuff. And it copies into the temporary file. The next is installer access your APK and copy your APK under the app folder. The next is it use your Unread manifest file and copy it to some other folders, which is important because the system doesn't need to access your manifest file over and over again. And also it creates a folder just for your application, which is under the data folder, which is used for the shared preference, storage, and other stuff. So now the installer does one more thing, because we have the classes Dex, but in order to start this process, the system needs to do something. The virtual machine needs to do something. And this process is not necessary for each time you run the application. So, so during the installation, it makes some optimization. So if you are using the Dalvik virtual machine, it uses the Dex bot and it optimizes your Dex file and copy it under the Dalvik cache. So basically your application, next time when it runs, doesn't need to do these things over and over again. And if you are using the Unread Runtime, it uses another tool, and during the installation, it translates all your code into the machine. So it runs faster. So that's it, actually. So now your application is ready for the use, and the user wants to start your application. It goes to the launcher, the home application, launch your activity, it runs the on-click, and it starts your activity. And when it starts your activity, it puts some information into intent, so the system will understand what you want to do. So it starts resolving your intent. And your intent contains intent action, intent data, and intent category. Basically, it has some information. So the system just resolves it. And in order to use it in the further steps, it just puts those information back to the intent. So it will be faster. And the next thing is, it checks the permission. If the user has enough permission for the target of the intent. And then it creates a new task, or depends on your flag. Let's assume that if you use the default, it will create a new task. And then starts the process. That's the good thing. Well, starting process, Unread has a very special process, which is called the zygote. When you start your device, it first loads the kernel, and kernel uses a special method which is called init. And this method just creates a process, start a process which is called zygote. And zygote also initiates the parent Dalvik. So why they initiate these things at first? Well, because it takes time. So they just make sure that it starts and on the run in the booting your phone. So next time when you want to access your process, it will be faster. And the runtime access this very special process and start communicating by using a socket. So we said that then the next step was the starting process. So first, application system checks that if you already started a process, so if it exists, it doesn't need to create a new one because it's consuming time. So it just uses the existing process. So if no, it doesn't start or create a new zygote. It just fork it. Because zygote and parent Dalvik use some shared library. So each time you fork it, it will be faster. So when let's say the process is started, everything is ready, every permission is ready. So the next step is the creating the activity thread. Well, activity thread is important because it manages your UI or the main thread. So it initiates the looper, which uses the message queue and handles your every like UI update and other stuff. Then after a while, and actually it happens in the same time, it binds your application, which is your application class. Then depends on your activity actually. Now it creates your new activity. So it happens in this step. Then if you're already familiar with this, Oncreate happens. In Oncreate, it inflates your resources, so it will be ready. And the onStart, users start seeing your interface, but cannot interact yet. And on resume, it's ready in the terms of everything. So user can interact, and user can do everything, actually. So it's basically this step. So we started writing code, and we ended up with displaying this screen. So we start writing code, we did compiling, we sign it, we put in the Play Store, we actually check the permission and other stuff. We learn a lot of bunch of things. Well, the question is, why do we need to know all of them? I mean, I could just use the assemble, and that's it. The rest will be done by the system and by the user. Well, the thing is, we need to increase the awareness. We need to know what we are doing. We need to know what we are doing because we could just do more stuff in writing our code or doing some resources. So you don't need to handle everything by yourself. You will know that your compiler will help you. You need to know that aligning is important. You need to know that signing your application is important. So then you will understand your tools. Well, basically we used to, for example, maybe most of us, Unread Studio. Probably we use only 10% of this studio. But on the other hand, Unread Studio is the Gradle. Gradle is a build system. And build system is the compilers. And build system is the aligning. So there are a bunch of stuff that's happening behind. And the next is, we have the certain answers. So when the user asks you, why my application size is bigger than, or in some phones, you may understand, well, maybe they use the different virtual machines. And you could understand why you have to write, for example, this code before the compiling. It's just, everyone just memorized that concatenating string is very fast because why? We just need to have these answers. Or why are we aligning? So to summarize, make the magic go away. So then we will have more control over what we are doing and we will know everything much better. So thank you, everyone. So any question?
You spoke about sync and align APK. I want to ask about Dex for jar debugging tools. Any debugging tools can convert APK synced or aligned to source codes, or we can reach resource other drawable or source codes. I want to ask about this.
Okay, so you are basically asking to reversing the Dex code into the Java. Well, the aligning doesn't involve anything with that. You could do that. You just need to care about if it is like using the ProGuard because of the obfuscation. If it is obfuscated, it will be harder to understand. But there are some tools, even for the obfuscation, you could just convert into the like a more human-readable code. Any other question? Yeah.
If I lost my key store, isn't there anything to do?
Basically, no. If you lost your key store, that's it. It's gone.
When is the DLLs in your APK loaded into your application? Like if you are using a shape library?
Well, it happens, actually, the question was when the DLL or the libraries are used by the system. It actually compiles before the Dex. So even your third-party libraries are compiled to Dex file. So this single file contains everything about your whole code. So in the terms of the runtime, there is no difference between library or your code.
What about the codes that are compiled into machine code? Like DLLs you wrote with C++ or things like that?
Well, it used the JNI. Well, it's the same. And it actually, it doesn't convert the Dex file. It happens in the runtime. So before the installation time, Dalvik used to put them onto the cache, and the Unread Runtime actually compiled into machine code as well. Since it's machine code, it just merged them into ELF file. Yes?
Does Sandbox provide security in Unread?
Well, actually, as a matter of fact, yes. Well, Sandbox comes from actually the Linux. Linux uses the user system, and each user cannot access the resources of another user. So Unread used this system in a different way. They apply this rule for each application. So each application has a user ID. So each application cannot access the other resources. Where there are some mechanisms, like using the IPC, you can access, but you need permissions.
Does it still exist with Art Runtime?
Yeah, it's completely different, actually. Runtime just run your application. Yes?
Having native code in our application would prevent security problem, like for example, having the Java code, and we can use Dex to jar so we can see the code, but having it native like C++,
they cannot access your native code. But, and for example, even if you have, for example, jar or something else, you could just load it in the runtime. They cannot access, they cannot reverse this code as well. But, I mean, if it is not so important, because using native is actually maybe good in the terms of security, but it's very hard for the maintaining or debugging. So if it is not very secure, like search algorithm or something, it will be better to use it in Java. Well, any more questions? Okay. Well, I have two things. One is for Android book, and one the Google board. So I will just give it the first and the last question. Thank you, everyone.